Okay, so today we need to wrap up a little bit of material we didn't get to last time on cloud computing, and then we'll do sort of a final course wrap up, and then we have evaluations, obviously. So remember last time we started talking about cloud computing, right? We introduced the idea of a data center, right? A big, huge warehouse of machines, and then we talked about, both some of the technology that goes into a data center, right, which is primarily virtualization we were talking about. Remember the idea to take a server and basically slice it into a bunch of virtual machines, which can each be running their own OS, their own applications, right? And then that kind of model is very useful when we're doing cloud computing and providing cloud services, right? Because then you can take big servers and sort of slice them up any way you want. We talked a few classes ago about RPCs as sort of an example of a programming model to write distributed systems. Something like a simple client-server application is sort of a very natural fit for that. And of course, you can also program machines in the cloud in the same way. But then there are other programming models which are sort of more oriented towards a cloud computing type environment, right? So for example, something like MapReduce, which is something that I'm sure some of you have used before, right? That was sort of the same idea that you did in Lab 2, right? Where it's sort of a model where it's very easy to scale up the number of machines running your application, right? And you don't sort of need to get bogged down in the details of communication between all of them because something like the MapReduce framework is basically designed to make your life as easy as possible, sort of run lots of machines and throw them all at the same problem, right? So that kind of model is very nicely suited to a cloud computing type environment. Now, some of the challenges that we have in cloud computing, right? We talked about sort of various models that cloud services often take, right? So for example, something like Amazon EC2 is just providing you raw machines, or something like Google App Engine is providing you some sort of software platform to write an application on. But of course, on the cloud computing provider, right, if you are operating the data center and you are basically managing 10,000 machines, right, there are challenges for you as well in how to actually handle that, right? So there are issues like if you are running arbitrary applications from different clients on your machines, right, you need to answer the question, well, how are you going to actually guarantee isolation between those, right? In some cases, that might not even be possible, right? If you're sharing physical resources, then maybe it's very difficult to actually prevent some kind of performance interference between multiple clients running on the same machine. So there are questions there, as well as how to actually scale up to that many servers, right? How are you actually going to maybe provide some administrative system such that you can handle 1,000,000 machines, right? So there's challenges like that. So for example, if you're Amazon and you're running an EC2 data center, and someone says give me a new medium-sized VM, right? Because as a customer, you basically just say, give me a virtual machine, and Amazon will provision you a virtual machine, right? So you as Amazon has to answer questions like, okay, where am I going to provision this, right? What server should I actually place this VM on, right? And those are not questions that the customer is answering. Those are essentially just left up to the cloud provider. Now, I want to talk about, we've sort of been talking at a very high level about how all of this works. To give you a sense of just briefly a few of the sort of technical challenges we run into, I wanted to talk about two specific examples. So the first thing I wanted to talk about was a little bit about memory efficiency, right? So we said that one of the nice things about using virtualization, right, is that you can have a single server and be running multiple VMs on top of it, right? And so each one of those VMs could be running their own operating system, right, with their own memory. But what might often be the case is you might actually have a lot of data in common between virtual machines, right? So if you have 10 different VMs that you're all running on one physical server, and maybe 8 of them are running Linux, maybe 8 of them are running even the same version of Linux, right? Then you essentially have potentially a lot of copied information. And all of your VMs are taking up some amount of physical memory, right? The practical limit to how many virtual machines you can stick on a single server is the physical resources you have available, largely memory, right? So you might have 10 different customers, each running the exact same web server, for example, and lots of duplication between them. Right, so what might we be able to do to actually increase our memory efficiency in an environment like that? Any ideas? Yeah. Store only one copy of the operating system. Right, so that would be great. Now remember, we do want to sort of give each, we want to give each VM essentially a complete system, so we don't want to necessarily say you can only run maybe this specific version of Linux. Right, maybe one person wants to run Ubuntu and one person wants to run Debian, which are two different versions of Linux, but they're actually largely derived from the same underlying code base, so they're actually quite similar. Yeah, you had a...
So do a copy on write sort of system?
Right, so yeah, exactly. So this gets back to the idea that we were talking about when we talked way back about memory management, and we talked about sharing pages. Right, so the idea is we're going to use this technique called content-based page sharing. And the idea is if we have multiple identical pages of memory across VMs, then we can basically map them to the same physical pages. Right, so if we just think about what a single system looks like, right, you have each VM is basically going to have its own page table, right, and each is going to have its own pages of memory. Right, so maybe we have two virtual machines, and each of them have, say, 3 pages of memory. And let's just say the letters and colors denote what the contents of that page are. Right, because each page is just a bunch of zeros and ones. It's just a bunch of data in that page of memory. And the hypervisor, which remember is essentially the core piece of software in a virtualization system that's actually managing the VMs, is taking those pages of the VMs and mapping them onto physical pages of memory. Right, so in this example, right, we have some duplicated pages of memory. Right, so we have 2 copies of page B and 2 copies of page A. Right, so essentially the hypervisor can detect those duplicates and remap them to the same copy. Right, this is exactly how we talked about 2 processes being able to share the same memory. Right, we said essentially we're just going to update the page tables to point to the same copy. Right, so we're doing the same thing here, only it's only in the hypervisor. Right, so the VMs themselves don't actually need to know that anything's going on. Right, because they are running, just as if they have a dedicated server, and then the hypervisor is managing everything else. Right, and so then by doing this, we have obviously freed up those other 2 pages of memory. Right, so now we've gone down from 6 pages to 4 pages of actual physical memory, and this could potentially mean maybe we can pack 3 VMs instead of 2. Obviously, real systems will have a lot more than 6 pages of physical memory, but that's the idea. Yes.
So from the user's perspective, if they have a virtual machine, they're using a virtual machine, and they're sharing. They're both 2 different people are pointing to the same place. Are they? Does it look like they're if a process takes up a bigger space?
Sure.
Does it look like they're using up a gig, or does it just look like they're using private gig?
From the perspective of the virtual machine?
Well, if you're using their Amazon's, if you're using Amazon and you're paying for 10 gigs,
sure,
and you're running Linux and it takes up a gig, does it take a full gig out of your space, or would it?
Yeah. So as an example, let's say that this is a machine with 2 gigabytes of memory, and let's say each one of these VMs has been given a gigabyte of memory, right? So they're each still going to say that they have a gigabyte of memory, even though we're actually using less than 2 gigabytes of memory. Right now, of course, this idea of copy on write is that if we have 2 VMs pointing to the same copy of this page A, and one of the VMs changes it, right, changes their memory, obviously the two copies are no longer equal. So we would have to actually make another copy of page A and basically split the 2, right? Because essentially what we're doing here is we're basically over-provisioning memory, right? We're saying that we're going to take the same amount of memory and pack it into fewer physical pages, right? So you do obviously need to be able to handle the case where you actually have to split those pages up after the fact, right? So that's sort of a balancing act here of if you over-provision all of your memory and then allocate every single page you have available, right? If you're not able to actually do any splitting later, then that's a problem, right? But this is actually a technique that can be used in moderation when you still have enough, so you have some extra memory to handle splits. Any other questions on this? Okay, and then second challenge I wanted to talk briefly about was this idea of dynamic workloads, right? So a very typical scenario we have is that a given application's workload may change drastically over time, right? So let's say you run some write some application and you deploy it to a virtual machine in the data center, and your application might see maybe 10 times as many users during the day as during the night, right? That might be a common situation. Or maybe an application gets a whole lot of users at once due to some unexpected event, right? So for example, if any of you are Twitter users, often what you see is when very popular events are happening and lots of people are using Twitter all at once, those tend to be the times when an application like Twitter has outages, right? Because it's essentially all of this massive usage all at once, right? So we might have something like this if it's, you're running a social media application, and you're basically, if this is just showing the number of users over time, and something happens like a really popular election that everyone's talking about, all of a sudden, right, you have a ton of users using your service. Right, and so what that means is that, obviously, in that case, you end up needing a lot more resources than you actually were probably given to start with. Right, because if you only have been needing this amount of resources, you don't want to basically upfront say, I want to pay for all of that. Right, and so that's potentially an issue we need to deal with. Because what we might have is a situation like this, where maybe we have a physical server with 4 virtual machines on it, and each one of those may be running some application, and maybe one of these applications gets this big workload increase. The physical server doesn't have enough resources to handle it all, and we basically want to move that somewhere else. Right, so this is the idea of migration that's often used with virtual machines, which is that we can basically pick up an entire virtual machine and actually move it from one physical server to another. Right, so in this example, maybe we have this server A that's overloaded, and we have this server B that only maybe has 2 virtual machines, and it has extra capacity. Right, so what we can just do is take this virtual machine, pick it up, move it from server A to server B, and now we've balanced the workload. Right, because remember, this is all, this is another nice thing that we can do because it's a virtual machine. Right, it's essentially just a software container that is simulating a physical machine. Right, the underlying physical hardware doesn't actually matter, it's just an abstraction provided. So, pretty simple idea there. Now, what might be a problem with sort of doing this in the obvious way, of just take this virtual machine, copy it from server A to server B? What might be a problem there? Yeah. Right, exactly. Main problem here is that if we do that in sort of the obvious way, right, we're going to have to basically stop the virtual machine, copy it from the source server to the target server, and then start it back up again. Right, and if we have stopped it to do that, right, while we're copying it over, the virtual machine's not running, right? So we've got downtime. And that's no good, especially when you're potentially doing this because your application all of a sudden has a lot more users, right? You don't want to basically say, we can't handle it, so come back in an hour, right? You basically want to be able to give yourself more resources without actually stopping your application. So we can actually do this using this idea of live migration, which basically means we're going to do the same idea of migrating from one physical server to another, but we're going to do it without actually stopping the virtual machine. So let's look at a simple example of how we can actually do this. Right, so let's say that our source virtual machine, our original one, has maybe 5 pages of memory. Right, so these are just pages of memory here. And we want to basically move the virtual machine from some source physical server to a different physical server. Right, and meanwhile, we have clients that are basically talking to the virtual machine, right, which is running some application. If you're running a social media application, you have clients interacting with that application. Right, so the first thing we're going to do is we're basically going to copy the pages of memory from the source server to the target server. And while we're doing that, we're going to continue running the virtual machine on the source server. We're not going to shut it down. Right, so we're going to start copying these pages one by one. And while that's happening, right, clients are still sending requests to the source server. Right, so we're just copying and running the application as normal. Right, so once we've done that, right, we have basically a copy of the application. We have a copy of the virtual machine on the target server, right, but it's out of date because some of the memory on the source server has actually changed in the meantime, right, because we've still been servicing requests. Right, so then the next thing we can just do is basically just update the parts of memory that have actually changed. Right, and in most cases, that's going to be much less than the total memory volume. Right, if you consider, maybe your VM is using a gigabyte of memory, and you copy that gigabyte of memory over from the source server to the target server, right, that's going to take, maybe a minute or two, over, a local area network that's pretty fast. And in that minute or two, some memory will change, but probably nowhere close to a gigabyte of memory will change, right? Probably some very small piece will change. So now we're just going to copy that, and while we're copying the small piece that changed, right, something else may have changed in the meantime, right? So you might have to do a few cycles of this, of just copying the changed piece, but ultimately you're going to get into a situation where the source server and the target server are almost identical, right? Not necessarily exactly the same, but very, very close. So then once we've gotten to that point, then we can basically take a little bit of downtime while we actually switch from the source server to the target server. Right, so the idea here is that once we're in this state where only a little bit is different, in this case we just have one page of memory that's different, right, as opposed to the 5 that comprise the virtual machine. So here we can basically stop the clients very briefly from talking to the source server, copy over that last page of memory. Once we've copied that last page of memory, the two servers are actually identical, right? And then we can basically, we're done, right? Because once the two are identical, we can essentially say, don't need the source copy anymore, and now basically the clients can just talk to the target server, right? And we have not stopped the VM at all, except for that last little bit where we actually performed the handover from the source server to the target server. Right, so this is basically a high-level picture of how live migration works, and this is actually a technology that is used in many current virtualization platforms. Right, so you can actually do something where people have run experiments where you're running something like a real-time game server. Right, and when you're thinking about game servers running, that's the kind of thing that players are not happy if your server stops responding for even a couple of seconds. Right, maybe a couple of seconds is no big deal if you're just trying to, post to Twitter and it takes you 3 extra seconds to do that. Right, but if you're playing a game, people don't want, the game to freeze for 3 seconds. But, this technique actually works very, very well, and you can actually switch a virtual machine from one physical server to another with potentially less than a second of downtime, a very, very small amount of downtime. Right, so pretty simple idea, but it works very, very well and allows us to basically take our VMs and move them amongst physical servers without actually imposing any downtime, without potentially the client even realizing that I was talking to this one physical server and now I'm talking to a different one. Right, so this is a very nice idea that we can do with virtual machines. Questions on how this is working? Okay. So that is pretty much everything I wanted to talk about cloud computing. So just to recap, some of the high-level points, right? So we've talked about, the core, key characteristics of what we mean by the cloud are, remotely available services, right? Typically located in, on shared infrastructure, which is typically a bunch of, huge number of machines sitting in a data center, right? This idea of pay-as-you-go. Right, because one of the nice things is that you only pay for the resources that you actually need and use, and if you're not using more resources, if you're using less resources at some time, then you'll be paying less money for that, right? And obviously the very high scalability, right? So if your data center has 10,000 machines, you can use as many of those as you want potentially, so you can very easily scale up to very, very large amounts of resources. Right, and then we talked about virtualization as this nice technology that's very often used in data centers to provide these things. And then I mentioned a few specific example challenges in doing resource management in a virtualized data center environment. Lots of others, but these are just sort of two nice examples. All right. Any questions about cloud computing before we move on? Okay. All right, so that pretty much wraps up our last topic. So I wanted to spend the rest of the time today just doing sort of a high-level wrap-up of what we've covered in the course, and things that hopefully are quite familiar, and anything that's not familiar, probably should go back and review. But first of all, just briefly about the final exam. So the exam is comprehensive. Right, basically anything that we've covered is fair game, from the entire semester. There will be some more emphasis on the last third of the course, topics that were not on the first two exams. So primarily that's file and I/O systems, distributed systems, and then the last few topics we've covered, protection and cloud computing. But you should be familiar with all of the material. So this basically gives us a high-level picture of what essentially we've covered in the course. So we had a couple of different main components, and largely what we've been talking about is the various hardware components of our systems and what the OS is actually providing to operate each of those components. Right. So when the hardware when we're talking about the processor, right, what the OS is doing is providing things like process management and scheduling, synchronization, all these things are provided via the user abstraction of the process, right? So we talked all about how processes are an abstraction used by the user, and that's provided by all of these various OS services, right? And then memory is obviously another key component of your machine, right? And the main abstraction there you're using is an address space. Right, and so what the OS is doing to provide that is doing all of the memory management, providing virtual memory, doing address translation. Right, these are all what the OS is providing to actually enable that abstraction. Right, we talked about I/O devices. Right, so all of the various I/O devices we use are all running with operating system support. Things like interrupt handling, and then of course the file system is an abstraction, or via files, which are sort of the user abstraction, right? We interact with files, and then files are part of the file system, which is obviously managed by the OS, right? And then we talked about distributed systems and some of the abstractions we use for those, right? Things like remote procedure calls, network file systems, right? Those are what users interact with, and those are all running with operating system support as well. So I was going to go through a quick recap of each of these topics. And feel free to stop me and ask questions at any point. Right, so highlights of process management. Right, so we talked about processes for quite a while. Right, a process is essentially just the execution state of a program. Right, so we talked about context switches are when we're switching from one program to another. Right, so you're obviously saving the running state of the current program, loading the next process by restoring its state, and then it can begin executing on the CPU. Right, we talked about the difference between processes and threads. Right, same idea, both essentially competing for execution on the CPU, but with threads, right, we're typically sharing the heap and code segment of a program. Right, processes were not sharing any memory. Right, we talked about user level versus kernel level threads. Right, two approaches to doing threading. Right, we talked about a number of different scheduling algorithms, right? Because we have lots of processes running on our machines. A typical machine might have a couple hundred processes running all at once, maybe only 2 or 4 processing cores. So obviously at any given time, right, we need to be deciding what process to actually run. Right, so we talked about a number of different scheduling algorithms, right, starting with the basic first come, first serve, right, round robin, shortest job first, and then multi-level feedback queues. Right, various pros and cons to each. Right, we talked about things like fairness and what jobs we're prioritizing. Right, so one of the things we talked about was that in general, right, we want to prioritize I/O bound jobs. right? So why was the reason for that? Why is it that we want to prioritize I/O-bound jobs in general? Yeah.
Because they affect response time roughly.
Right, so they affect response time. So what does that mean for utilization? Yeah.
They also take up the CPU less because they're going to I/O.
Right, they will take up the CPU less because they're going to I/O. Right, so the idea is that if we have jobs that are I/O bound that are mostly doing I/O, we can basically give them the little bit of CPU time they need immediately, which will enable them to then go off and continue doing I/O. Right, because while they're doing I/O, they're not waiting on the CPU. Right, our system utilization is basically increased. Because ideally, we basically want complete utilization both of the CPU and whatever I/O devices are being used, right? So in general, we want to favor I/O-bound jobs, right? And so that was sort of one of the ideas of when we talked about multi-level feedback queues, right? What we're basically trying to do is favor those I/O-bound jobs. Right. Then we spent a couple of classes talking about synchronization. Right, so there we had basically three primitives. We talked about locks, semaphores, and monitors. Right, we talked about both how we actually use those constructs, as well as from an OS perspective, how we actually provide support for them. Right, so we talked about things like atomic instructions and disabling interrupts as techniques that actually allow the OS to provide these useful primitives. Right, so it's not just how we can use them as programmers, but also what does the OS need to do to actually ensure that they work as we know. Right, so we talked about three different things a semaphore could be used for. Right, so we had mutual exclusion, access to a shared pool of resources, and imposing scheduling constraints. Right, so we talked about a couple of different things we can use semaphores for. Right, this idea of condition variables. Right, where you can basically go to sleep and give up the lock at the same time. Right, that was the idea of a condition variable. And then we talked about deadlocks for most of a class. Right, so we talked about necessary conditions for a deadlock to occur. What we can actually do about deadlocks. Right, we can either wait for them to happen and then break them, or we can basically prevent them from happening by ensuring that one of the four necessary conditions never holds. Or we can basically just sort of do runtime checks using something like Banker's algorithm, right, where we're basically going to prevent deadlocks at runtime by saying whether this resource allocation could actually lead us to a deadlock or not. Right, so then we moved on to talking about memory management. Right, so remember we started talking about contiguous allocation. Right, either static or dynamic relocation was essentially what we started with. Right, and we said that this is very easy and straightforward and nice, but we're going to get a lot of external fragmentation. Right, that was the big problem. Right, and we could potentially address it by using something like compaction, but that's typically going to be really expensive. Right, so the solution we proposed was take our memory, chop it into fixed size frames, our physical memory, and then programs are basically just going to allocate pages of memory which will be mapped onto physical frames. Right, so that was the idea of paging. Right, so then each process has a associated page table. Right, address translation. The addresses now are including a page number and an offset that are allowing the OS to actually do that address translation. Issues of efficiency. Right, so we talked about one of the issues with the page table. Right, is that you're now using multiple memory accesses. Right, if you have to go to the page table, which is sitting in memory, in order to do an address lookup, right, that's essentially doubling the access time of memory. Right, so to address this, we introduce some extra hardware. Right, we've talked several times throughout the course about how oftentimes we're basically using hardware support to compensate for efficiency reasons. Right, so in this case, we use the TLB to basically store page table entries so that we could retrieve them very quickly, so that we're not always having to go to the page table in memory. And so remember, the TLB, as in many other hardware-assisted things we've talked about, not actually necessary for correctness, but does actually make our approach much faster. Right? So paging doesn't need a TLB to work, but it does need a TLB to work efficiently. Right? So then we moved on to talking about demand paging. Right? So remember, the idea there was again, we could have tons of different processes, and they're not just competing for the CPU, they're also competing for memory resources, right? And we said that we don't want to have to enforce that all running processes can fit in memory at once, right? That's typically not going to be the case, right? So instead, we can basically just go and take all of our processes' memory, store them on disk, and then fetch them on demand when we actually need them, right? That's what we mean by demand paging. And so then obviously we talked about page faults quite a bit, right? So a page fault is when you essentially need to use some memory that's not currently in physical memory, that's sitting on the disk, so you have to go and fetch it. We talked about page faults being very, very slow, but demand paging is still usable due to the 90-10 rule, so which hopefully you all remember from exam 2. And then to minimize page faults, we talked about a number of different page replacement algorithms. Remember, so the objective, essentially, of a page replacement algorithm is to minimize the number of page faults you get. And we saw examples of how a bad page replacement algorithm can lead to many more faults than a good page replacement algorithm. Right, so we talked about a few different examples, right? FIFO, min or opt, LRU, right? And so then we talked about how we can actually implement LRU, right? So remember, min or opt was sort of the optimal case where you're looking into the future to see, what is the best page to actually replace, right? In practice, we can't actually do that because we don't know what we're going to be predicting in the future, what we're going to be requesting. So LRU is essentially saying, least recently used, let's assume the past predicts the future. Now that was still, challenging to actually implement exactly. So then we instead use approximations, right, like second chance. Right, so various advantages and disadvantages to each of these schemes you should be familiar with. So then we talked about I/O systems for a few classes. Right, so this was largely talking about how device drivers work. So remember, our simple picture of how a device driver works is basically 4 registers. Right, so you have a command register, a status register, and then data in and data out. Right, and then when you want to write to a device driver, you're basically just setting the data out and command registers, and then the device driver basically hands that off to the device itself, which will actually go and execute the command. And then when you want to read from the device, you're just reading from the data in and status registers, right? So that's essentially the simple idea. And we talked about how we can implement device drivers. Using polling was sort of the basic approach, but it's not super efficient because it involves a lot of busy waiting, right? So instead, we're going to use an interrupt-driven approach, which is what essentially all of our systems use. And then we talked about efficiency in I/O systems. Right, so in the basic approach, you're essentially doing reads and writes 1 byte at a time, which is really, really slow. So we talked about how we can do something better for a device like a graphics card or a disk that's doing a lot of bulk I/O is using DMA, direct memory access. Right, so that's basically going to let us do reads and writes in bulk, and also not have involve the CPU on every single read and write that we want to do. We don't have to do it 1 byte at a time. We're just going to hand it off to the DMA controller, say, go do your read and write of a lot of data and stick it in this, part of memory. Right, so then we talked for a while about disks, right? So we had our picture of how a disk is actually, what a disk looks like physically, right? So we have a bunch of surfaces. Each surface is divided into tracks, right? Each track is divided into sectors, right? Sectors are sort of the basic unit that we're doing disk I/O on. And then, right, when we're actually reading and writing from the disk, right, we talked about the various components of overhead, right? So we had, seek time, rotational latency, and transfer time, right? And of the 3, transfer times when we're actually getting useful data or writing data, right? Seek time and rotational latency are essentially just wasted overhead. Right, so we talked about disk scheduling algorithms are what we do to actually minimize seek time and rotational latency. And so we talked about a couple of different algorithms for doing disk scheduling. Right, again we started with FIFO, SSTF, right, shortest seek time first, and then
For SSDF.
Yeah.
With 2 different, so you're at 50 and
Yeah.
you go 51 to 49.
Yeah.
Which would you choose?
It doesn't really matter. Right. So the question was, if your disk is at track 50 and the next request is at track 49, but you also have a request at 51, how should you order those? Doesn't really matter. I mean, again, you could maybe you could modify your algorithm so that you do shortest seek time first and look one step into the future to decide, well, if I went to 49, then what would I do? Versus if I did 51, then what would I do? But sort of the basic idea, you could pick either. But then we talked about one of the algorithms that's actually often used in disks is the scan algorithm, right? So that was basically the elevator. Right, so where you are basically scanning back and forth across the tracks of the disk, servicing requests as you hit them. Right, so that was the elevator or scan algorithm, and then the slight modification of that was the circular scan, right, where you're essentially after you get to the end of the disk, once you get if you have tracks 0 to 100 on your disk, then maybe you're going from 0 to 100, and then once you hit track 100, you reset back to track 0. Right, and then we said that ensures a fairer distribution of request times, regardless of whether a request is in the middle of the disk, at track 50, or at the end of the disk at track 95, for example. And then we talked a little bit about caching and buffering. Right, so the idea here was that I/O devices are very, very slow. The CPU is very, very fast. So we essentially need to handle the mismatch there. By allowing the I/O devices to basically fetch bigger pieces of data before we necessarily actually need them, and then we are basically not having to constantly wait for the I/O device to catch up later. And then we talked about using some other performance enhancement, things like disk read ahead, right? So there the idea was essentially that the disk can read in more data than we actually requested, just because the disk is constantly spinning, so we might as well just read that data while it's there and essentially free to read. And then hopefully later we'll actually request that data and we'll already have it available. So we talked for a while also about file systems, right? So we talked about what is a file, right? A file is essentially just a named collection of data, right? It's just data that you've given a name. Right? A directory is essentially just taking a file name and mapping it to a file ID, right? So your OS is just storing all of your files. Your files have names, but internally your OS is just identifying your file by typically an integer, right? So a directory is basically saying, here's a file name, give me what the actual file ID is, so that the OS can actually look it up. Right, so then we talked about what types of metadata do we actually need in a file to support the different types of file access we do. Right, so what were the two types of file access that we want to support? Yeah. Right, random and sequential. Right, those were the two main types of access. Either you want to just read start to finish, or basically jump around in a file. Right, and so we talked about allocation techniques that will allow us to do that. Right, so we started with contiguous allocation, where you're just picking some place on the disk to store the file and just laying it out continuously. Right, and that's nice because then the only metadata we're storing is essentially where the file begins. But obviously, for a very large file, you may not actually have that much contiguous space available. Right, so then we talked about using a linked list approach where you have blocks of the file pointing to the next block, right, which means that we don't have to worry about fragmentation, right, but random access is potentially very slow because you have to traverse through the linked list. All right, and then we talked about using an index structure, right? So in Lab 3, right, you were basically doing a file system with a single level index structure, right? So right, and in Unix, we'll use a multi-level index structure, right? So the index structure is basically just a bunch of pointers saying here's where each block of the file is located, right? So maybe you have 100 different blocks of the file, so you have 100 pointers in your file object, and if that's very, very large, if you have a very large file, then potentially you're having to store lots of metadata to store all of those pointers. Right, so then we talked about using a multi-level index to basically solve that problem, right, where you have essentially entries in the index pointing to other indices, so potentially multiple levels of that. And we said that that's essentially how Unix does things, how most current file systems are using a multi-level index structure. But then remember, we also talked about even these simpler approaches, right? Something like contiguous allocation, right? Very straightforward, and we said that actually still used on something like a CD, right? Something like a CD where you're just writing once, and then you're never going to actually move things again, right? Contiguous allocation, a very simple approach, is actually the best approach there, right? Because then you're getting fast access, and you don't have to worry about fragmentation because data is never actually changing after you lay it out on the CD. So then, more recently, we've been talking about distributed systems, right? So we said the distributed system is basically, a collection of CPUs cooperating over a network to achieve, some shared goal, right? So, big systems like Google are examples of distributed systems, as well as, simple client-server applications, something like email is a distributed system, or a web server where you have a client talking to a web server. And then we talked about this distinction between a parallel system and a distributed system, right? So a parallel system is basically tightly coupled, right? If you have a bunch of CPUs that are all sort of part of the same physical machine and communicating over a system bus, right? A system bus is very fast. That's essentially a tightly coupled parallel system versus a distributed system where we are typically communicating over a relatively slow network, right? So we essentially have logically, we have independent machines that are all communicating over a network. Right, and so benefits of distributed systems are things like resource sharing, right? So you can access resources that are not on your local server or attached to your local server, right? Scalability, right? So if you have an application that needs a lot of resources, you write a distributed system to allow your application to use 1,000 machines if you need to. Fault tolerance, right? So if you have a distributed application that's running on 1,000 machines and 5 of those machines go down, right? You can still potentially handle that without actually any service downtime. And downsides primarily that we deal with distributed systems are complexity, right? So there's a lot of added complexity for actually writing distributed applications, as well as things like security problems. And then we talked about different types of migration, right? So we talked about data migration is when we're moving data to computation. So for example, when you're working with a distributed file system, right, all the computation is happening on your machine, right? If you search for data in a distributed file system on your laptop, right, you're basically going and fetching the data from the network file system, bringing it to your machine, and then performing the computation there, right? So that's data migration. And then the opposite idea is, computation migration. And we said, a good example of that is something like a web search query, right? Where when you're performing a web search query, it's essentially a massive index of web pages is being searched for your query. But you don't actually say, give me the index, and then I'll search it on my local machine. You're basically just sending your computation is basically just a little search query. You send that to the data, and then it will actually be searched there. So we talked a little bit about sort of a high-level picture of networking, sort of in the context of distributed systems, right? So we talked about different types of networks. We have local area networks, which is something like the network you might have in your your home, or the network that you might have in a department. The CS department has a local area network, right? And then wide area networks is where you have much larger geographic regions and much slower connections typically, right? So the best example of a wide area network is the internet. We talked about number of different network topologies, right? So they each had different pros and cons, right? Some of them were very fault tolerant, but too expensive. Some of them were very easy to do, but not very fault tolerant, right? We talked about the idea of a single point of failure as being an issue in distributed systems, right? So the idea there is if you have one system one machine that your entire distributed system is reliant upon, then despite the fact that you might be using 1,000 servers, if that one important server goes down, if that takes down your whole system, right, then that would be an example of a single point of failure. Right, then we talked about what is a network protocol stack, right? So example, the example that we went into a bit more detail there was TCP/IP, right, where you have a network stack, a bunch of protocols starting from all the way down at the physical layer, where you're basically sending bits on a physical wire up to the application where you're actually sending messages at the level of a web browser, say, right? And so TCP/IP is an example of one of those protocol stacks for handling communication between machines. Right, we talked about RPCs, remote procedure calls, as a way to write distributed applications. Right, so essentially RPCs, the idea is that you want to be able to call procedures just as if you were writing a standard, non-distributed application, but the code might actually be located on some other server. Right, so RPCs are basically allowing us to write programs very easily where you're basically dispatching methods to remote servers without having to worry about all of the details of network communication yourself. Right, so we talked about how an RPC system actually handles that. Right, we talked about the idea of stub code, which are basically what the system provides you to actually handle those networking details. And when you write your application, you basically don't need to worry about any of that. And we gave Java RMI as an example of an actual implementation of an RPC system. And we looked at a few simple examples of how to actually write an RMI program. Distributed file systems we talked about for the better part of the class. Right, so we had these important ideas in distributed file systems about location transparency versus location independence. Remember, so the idea here was that location transparency is when we're naming a file, right, the file is located on some machine in our distributed file system, right, because the idea is that now the data is stored on some other server. So location transparency is basically that a file name doesn't reveal what server a file is actually located on. Right, so if you look at the file name and the file name tells you, this file is actually sitting over on, server A somewhere, then that would not have location transparency. Right, but we talked about, looking around in, NFS, if you're on an EdLab machine and you're in your home directory, the file name just looks like a regular, directory name to your file. And that doesn't actually say anything about where the file is actually located, even though it may be located on some, network file server. And remember, that was different from the idea of location independence, which is saying that the file name doesn't actually change if we move the file. Right? So if the file name can basically be the same regardless of where it is, then that we can say that has location independence. Right? Then we talked about caching in distributed file systems. Right? So the issue there primarily was one of consistency. Right? Where if you have a file sitting on a distributed file system and multiple clients are working with that file, right, caching is good for performance, but we don't want to run into cases where we have caches with inconsistent copies. Right? So remember we talked about different approaches to handling that. We can either say the central server can basically handle all of that to ensure consistency, or we can basically just leave it up to the clients to handle consistency themselves. And then we talked about the difference between write-back and write-through caching, right, which essentially determines when you update a cached copy, do you actually go and update the underlying copy not in the cache immediately, right? And doing so is much slower to do that because you have to actually go over the network. So that's going to be slow, but it's going to help with things like reliability, right? Because if you actually defer that write until later and your system goes down, then you may actually potentially lose data from doing that. We talked very briefly about protection, right? So the problem in protection was ensuring that only the right users or right processes can access certain resources. So the way we talked about this was this idea of a domain, right? So a domain is essentially a set of access rights saying what user has access to what resources and what operations can they perform on those resources, right? So the way we describe that, you can essentially specify the entire protection policy using this domain access matrix, right? Which is essentially all of these sets of domains and all of the sets of objects and the operations that are allowed for a given domain on a given object. Remember, we said that the problem with that was that the domain access matrix could potentially be really, really big. So our OSs are typically not actually storing this huge matrix saying, what can each user do with each object, right? So typically in a real OS, a domain is usually some user, right? So you as a user can access some files, can't access some other files, right? In that context, the user is essentially the domain, and the files are the objects that would be in this, domain access matrix. And so, typically the way we're actually implementing this is either access control lists, right, which are basically storing columns of the domain access matrix, right? So that's, for a specific file, who can access this and in what way, right? So that's the access control list approach. And the other approach that's not typically used, but we talked about a little bit, was what we called capability lists, right? That's essentially where we're storing rows of the matrix, right? So then if I say, you as a user, here's all the permissions that you actually have. Here's everything you're allowed to do, right? That would be an example of storing things in the capability list. Now, typically we use the access control list approach, but those are two, the capability lists are an alternative. And then, finally, we talked about cloud computing, which we most recently covered, so I won't belabor the point. But obviously, we talked about what is a data center, what do we mean by virtualization, how is it useful, and what do we mean by cloud computing, and what are some of the challenges that arise there. Just some general things for the exam. You should have a sense of how different parts of the OS impact one another. You won't be asked to read or write actual code, but pseudocode is still fair game, and won't be any really detailed questions about a specific operating system. Right, we're primarily just concerned with general concepts in OSs.